It is an effective and general approach and is most commonly used for density estimation with missing data, such as clustering algorithms like the GMM model. So we can treat it as a general approach which can be used for density estimation in order to find out the missing values or missing data. Problem of latent variables for maximum likelihood, right? So I hope that it is clear to you that what are the latent variables and what is the maximum likelihood estimation. A common modeling problem involves how to estimate a joint probability distribution for a data set. So density estimation involves selecting a probability distribution function and the parameters of that distribution that best explains the joint probability distribution of the observed data. There can be many techniques for solving this problem, and the most commonly used problem for density estimation is the maximum likelihood estimation, right? So these are basically the same, more or less the same things which I have discussed in the previous slides. So the maximum likelihood estimation involves treating the problem as an optimization or search problem, right? So you can also say that it is a heuristic or a search problem where we seek a set of parameters that results in the best fit for the joint probability of the data sample, right? So we are looking for the parameters, or we are looking for a set of parameters which can basically best fit for the joint probability of the data sample. So let's have a look again at the latent variables. A limitation of maximum likelihood estimation is that it assumes that the data set is complete or fully observed, right? So a fully observed data set will only be the case when the data set is fully completed. And one limitation of the maximum likelihood estimation is that it assumes itself that the data set is complete or fully observed, which might not be the case in most of the circumstances. This does not mean that the model has access to all data. Instead, it assumes that all variables that are relevant to the problem are present, right? So the assumption which a maximum likelihood estimation is making is that it is assuming that all the variables are present. But as I told you, that it might not be the case for all the situations and circumstances. This is not always the case. There may be data sets where only some of the relevant variables can be observed, right? So there can be some variables which are observable, and there can also be some variables which are not observable. Although they influence other random variables in the dataset, they remain hidden, right? So since they are not observable, that's why they are hidden, but they have an impact or they have an influence on some other random variables. More generally, these unobserved or hidden variables are referred to as the latent variables. So we can define latent variable as the hidden or unobserved variables, but they have an impact or they have an influence on other random variables. So the limitation of maximum likelihood estimation is that the conventional maximum likelihood estimation does not work well in the presence of latent variables. So if we have hidden variables or latent variables or the variables which are not observable, then in that case, if we use maximum likelihood estimation, that it will not work perfectly. If we have missing data or latent variables, then computing the maximum likelihood estimate becomes hard. So it will become an NP-hard problem if there are missing data sets, missing values or latent values, and we are trying to calculate the maximum likelihood of it. Instead, an alternate formulation of maximum likelihood is required for searching for the appropriate model parameters in the presence of latent variables. And what that alternative is, that it is the expectation maximization algorithm, which is also termed as the EM algorithm, and we use such kind of approach or such kind of algorithm when we have the issue of latent or missing values. So here are the basic steps of an EM algorithm. The EM algorithm is an iterative approach that cycles between two modes. So there are two basic modes. The first mode attempts to estimate the missing or latent variables, and this mode is known as the estimation step or the E step, right? So in first mode, we are trying to figure out the values for the latent variables, or we are trying to estimate the missing values, and we are referring this step as the E step or the estimation step because we are trying to estimate the missing values here. The second mode attempts to optimize the parameters of the model to best explain the data, and this is known as the maximization step or M step. So in M step, we are basically trying to optimize the parameters because we have already the values through the E step. So in M step, we can optimize our model and we can have the most suitable parameters that can best fit the data set. So there are two main steps. One is the E step and one is the M step. The E step estimates the missing variables in the dataset. The M step maximizes the parameters of the model in the presence of the data. The EM algorithm can be applied quite widely, although it perhaps most well known in machine learning for use in unsupervised learning problems such as density estimation and clustering. Perhaps the most discussed application of EM algorithm is for clustering with a mixture model, right? So we can use for a number of clustering algorithm applications, we can use this algorithm. So a Gaussian mixture model, which is also known as GMM, and the EM algorithm. A mixture model is a model comprised of an unspecified combination of multiple probability distribution functions. A statistical procedure or learning algorithm is used to estimate the parameters of the probability distributions to best fit the density of a given training dataset. So in GMM or the Gaussian mixture model, we use a combination of Gaussian probability distribution, which you already know that we have a bell-shaped distribution which we refer to as the Gaussian or normal probability distribution, and requires the estimation of the mean and standard deviation parameters for each. So for each of them, we need to calculate these two statistical measures, which is the mean and the standard deviations. There are many techniques for estimating the parameters of a GMM, although a maximum likelihood estimation is perhaps the most common. So most commonly used model in order to estimate the parameters of GMM is a maximum likelihood estimation. Now consider a case where a data set is comprised of many points that happen to be generated by two different processes, right? So consider a situation here in which we have two different processes and we have a number of points belonging to a data set which are being generated by these two different processes. The points for each process have a Gaussian probability distribution, but the data is combined and the distributions are similar enough that it is not obvious to which distribution a given point may belong. The process is used to generate the data points represent the latent variable, right? For example, we have two processes, 0 and 1, and these processes which are being generated, the data sets, these are the latent variables. It influences the data but is not observable. So we have seen that they have an impact on the data, but they are not observable. As such, the EM algorithm is an appropriate approach to use to estimate the parameters of the distribution. So now let's have a detailed look and have a look at its algorithm itself in order to estimate, in order to have a look at the EM algorithm. In the EM algorithm, the estimation step would estimate a value for the process latent variable for each data point, and the maximization step would optimize the parameters of the probability distributions in an attempt to best capture the density of the data. So the target is to best capture the data density. The process is repeated until a good set of latent values and a maximum likelihood is achieved, right? So the target is to have a good estimate of the latent values and a maximum likelihood so that it can best fit the data. So we have two steps, E step and M step. E step is for estimation and M step is for the maximization, or the in order to figure out the best parameters for the model. We can imagine how this optimization procedure could be constrained to just the distribution means or generalized to a mixture of many different Gaussian distributions.